All right, so today I want to wrap up the sections 6.2 star, 6.3 star, and 6.4 star. I want to talk about all of them together today and sort of come to a closure of the discussion of the logarithm functions and the exponential functions. A couple of years ago, I went to one of the conferences, and one of the speakers was speaking about jobs for math majors and stuff like that, people in mathematical sciences. And one of the examples that he was giving is that about this company named Raytheon. How many of you have heard about Raytheon? Raytheon is a company. They are in, I think, they are in robotics or something. And so in one of they were hiring new graduates in engineering and mathematical sciences. And in one of the interviews, they asked, they had most of the candidates were engineering, and there were 2 or 3 students who had degrees in mathematics. And one of the questions that was asked is that if the hour hand of the clock is at 2, I think, and if the minutes hand is at, a little bit below 4, what's the angle between the 2 hands? What's the angle between the 2 hands given the positions of the 2 hands? And most of the engineering students, they went into the interview room, they came out very quickly. It seems like they answered that question very, very quickly. Okay? They gave very quick answers to that question. And then it seems like the math majors, they went into that, they struggled with it, they took a lot of time, and they came out, they stayed at the interview longer than most of the engineers did. And it turned out that actually the math majors got the answer to this question correct, and the engineers, they didn't get that answer correct, even though approximately their answer was correct. Am I making sense? You can give an approximate answer very quickly, but to give an exact answer, you need time to think about it and give an exact answer to it. I'll let you think about that if you want to think about it. But my point is, what's the difference? Why, so it's like some people had the training to think more deeply inside a problem than the others. Okay, that's what it came down to. I'm not saying the math majors were special. All I'm saying is that different people think about problems differently. Okay. And usually, if you have done math for a long time and if you're good at math, you can deeply think about a problem, struggle with it, but you can go through a process and come up with a solution. You understand that process better, and that's because you as a math major, you want to look at some nitty-gritty details of that problem than the others. Again, I'm not saying there are a lot of engineering students who are very good at math, and I have seen in grad school a lot of my friends in engineering were sometimes, in fact, better at math than so many of the math majors. Okay, but I'm saying some people who are better at math and who have a better training in math, they can look at this nitty-gritty technical details better. They have an eye for that. And so, why am I saying that? Is because I'm going to look at some of the when I try to come to a closure with these sections, I'm looking at some nitty-gritty stuff. Okay, nitty-gritty details, technical details here and there. And if you understood everything that we did so far, you're okay. Take a nap for the next 50 minutes. You'll still be okay. But if you're inclined to look into the nitty-gritty details, think about the nitty-gritty details, then you can pay attention. So first of all, remember how we define powers. Powers. Let A be a positive integer, let A be a positive real number, and let m and n be any positive integers. I want to once and for all talk about what does it mean to raise a to different exponents. So what do we mean by a to the power 0? It means 1. What do we mean by a to the 1? It means a. What do we mean by a to the 2? It means a times a. In general, what's the meaning of a to the n for any positive integer m? Well, it means a multiplied with itself n times, right? It is a to the n minus 1 times a, or a multiplied with itself n times. Okay, now we have a meaning for, now we understand what it means to raise a to a positive integer. What does it mean to raise a to a negative integer? So what is a to the negative 1? A to the negative 1 means 1 over a. 1 divided by a. What does it mean to raise a to negative n? It means 1 divided by a to the power n, or it means 1 divided by a to the n. 1 over a to the power n, or 1 over the nth power of a. Okay, so that's the meaning of a to the negative n. So by that we have now the meaning. So what do we? So now we know what we mean by raising a to a negative integer, right? Positive integer, negative integer. Now, what does it mean to raise a to a rational, positive rational integer? For that, first of all I need, what does it mean to raise a to 1 over n, where n is a positive integer? Well, the meaning of a to the 1 over n is that it is the positive real root of the equation x to the n minus a equals to 0. So this is called the nth root of a. Nth root of a to the 1 over n, is the positive real root of the equation x to the n minus a equals to 0. X to the n minus a equals to 0 means what? Same thing as x to the n equals to a, right? So the positive real root of that equation is called the nth root of a. Now, how do I know that equation has a positive real root? Well, I know that because if you look at the function x to the n minus a, that's a polynomial continuous function. It has a negative and a positive value. Okay? I'll let you think about that. It has a positive negative value. So because it's continuous, if it has a positive value, negative value, the graph has to go through the x-axis. And right there it has a real root, okay? Now, so now I have a meaning for the nth root of a. Once I have the meaning for the nth root of a, what's the meaning of a to the power m divided by n? Well, it means I take the nth root of a first, and then I raise it to m. M is a positive integer. So a to the m over n is a to the 1 over n, and then you raise it to m. It means you multiply the nth root of a m times. Once I have the meaning of a to the m over n, where m and n are positive, it means I understand what it means to raise a to a positive rational number now. So now, what does it mean? What do we mean when we raise a to a negative rational, negative m over n? Well, it's just 1 divided by a to the m over n. I have a meaning for a to the m over n, and I just take the reciprocal of that. So once I have done that, I have a meaning for the following. What does it mean to raise a positive number a to any rational exponent? I understand what that means by this discussion. I gave you a definition of what it means to raise a to a rational exponent. That's the bottom line. Is everybody okay? This is independent of the exponential log function, right? I didn't talk about exponential log function here. This is an independent meaning of a to the power r for any rational number r. So keep that in mind. And now get into the logarithm and the exponential. I'm going to start from the very beginning. What's the definition of ln of x? The definition of ln of x is the integral from 1 up to x of 1 over t dt, and we make that definition for x greater than 0. Essentially, what's the meaning of ln of x? Well, when x is larger than 1, ln of x is giving you the area below the graph of 1 over t above the interval from 1 to x. That's the meaning of an integral. Okay? So essentially we are defining the ln x function as the area below, in terms of the area below the graph of 1 over t. We have defined ln of x function essentially in terms of the area below the graph of 1 over t. Is everybody okay? Now, by applying the fundamental theorem of calculus right away, this is an integral function. We know how to find the derivative. And the derivative is what? The derivative of ln of x would be basically the integrand evaluated at the upper limit x. So the integrand evaluated at the upper limit is 1 over x. So the derivative of ln of x is 1 over x. If I take the second derivative, I get the negative 1 over x squared. And also I showed to you, if I take the derivative of ln of absolute value of x, that is equal to 1 over x. Now this makes sense as long as x is not 0. This also makes sense for negative x, because when I take the absolute value of a negative x, I get positive, and I can apply log to it. But I cannot apply ln to 0. Is everybody clear? So we did those the derivative formulas, and also the corresponding integral formula is that what's the integral of 1 over x? The integral of 1 over x is ln of absolute value of x plus c. Why do I write absolute value of x? Because I want to include the case where x may be negative. Now, if I assume that x is positive, I don't need that absolute value sign. So I can say the integral of 1 over x is ln of x if I assume x is positive. Clear? Okay, I am putting absolute value to allow negative values of x. Now, once I have the derivative formulas, now we know that we have this nice logarithm. In fact, the very reason for having the log function are these three properties. Okay? I can show you that there is one and only one function that satisfies 1, 2, and 3. Okay? Together with some constraint like ln of e has to be 1. Okay? But ln, so what are the properties? Ln of xy is ln of x plus ln of y. Ln of x over y is ln of x minus ln of y. Ln of x to the r is r times ln of x. Now here, x and y are positive. R is a rational number. Why do I say it's a rational number? Why am I restricting the exponent r to a rational number at this stage? Number 3 actually works even when r is real. We're going to see that in a bit. But at this point, why am I not telling you that? Well, I'm not telling you that because I haven't given you a meaning of x to the r when r is irrational, right? Am I making sense? At this stage of development, I don't know what does it mean to raise x to an irrational exponent. That's why I'm saying number 3 works for rational exponent only at this stage, but later on we're going to change that. So ln of x to the r is r ln of x. What I want to do now is give you a proof of number 3. Remember I said you can prove these things by using derivative. Now how? I want to show in number 3 the left hand side is equal to the right hand side. I want to show two functions. On the left hand side I have a function of x. On the right hand side I have a function of x. I want to show they are the same. One way to show that is show that they have the same derivatives. Now if you have two functions, if they have the same derivatives, if two functions have the same derivatives, right? What does it mean? They are antiderivatives of the same function, right? If two functions have the same derivatives, then they are both antiderivatives of the same function. It means that they differ only by a constant. So I want to show that the two sides, they have the same derivatives. So take the derivative of the left hand side. The left hand side is ln of x to the r. If I take the derivative of that by using the chain rule, what's the derivative? Well, if x to the r were just x, then the derivative would be 1 over x to the r. but XODR unfortunately is not just one. XODR is not just X, so you have to multiply by its derivative, and if you multiply by its derivative, you get R divided by X. This is by chain rule. So by chain rule, the derivative of ln of x to the r, 1 over x to the r times r x to the r minus 1, which is r over x. That's the derivative. What's the derivative of the right-hand side? The right-hand side of number 3 was r ln of x. If I take the derivative of that, I get r divided by x clearly. Why? It's r times the derivative of ln of x. Derivative of ln of x is 1 over x. R is fixed here. So that's the derivative. So they are the same, r over x, r over x. So I know that the derivative of ln of x to the r is the same as the derivative of r ln of x. I was trying to prove the identity number 3, okay, and I showed that they have both sides have the same derivative. So then, if they have the same derivative, it means that ln of x to the r differs from r times ln of x by what? If two functions have the same derivative, they only differ by a constant, period. If two functions have the same derivative, they only differ by a constant. Okay? Well, what's the value of c? I claim c has to be 0. Why? Well, plug in x equals to 1 to get, what's the left-hand side when x is 1? When x is 1, the left-hand side is log of 1 to the r. Log of 1 to the r is log of 1, which is 0. On the right-hand side, I get r times ln of 1. R times ln of 1. Ln of 1 is 0, so I get 0 plus c, which tells you c has to be 0. And so I can finally say ln of x to the r is r ln of x. The exponent r can be moved in front of the ln. That's the conclusion. Is everybody clear? You can prove all the other laws for ln function in the same way. Take the derivatives of both sides, show that they are the same, so that they differ by a constant, and then show that the constant is 0, and you're done. That's how the proof works. Okay. Once I have the ln function, what's the graph of the ln function? Remember, we showed that we looked at the first derivative of ln, second derivative of ln, so we know exactly how the function ln is increasing, how it is concave up and down, and we also know what's the limit as x goes to infinity, and what's the limit of ln of x as x goes to 0. We know the function ln is increasing concave down because we know the derivatives exactly, and we know that ln of x goes to infinity. As x goes to infinity, it goes to negative infinity as x goes to 0 from the right. We know the graph, which is the pink one in my picture. And now we defined the number e to be the special number e for which ln of e is 1. Right? Okay, the ln function is 1 to 1, so it has an inverse. What's the graph of the inverse of ln of x? Well, I look at the line y equals to x, and I flip the graph of ln of x about the line y equals to x. That is, I look at the reflection of the graph of ln of x across y equals to x, and I'm going to obtain the graph of the inverse. And we are calling the inverse of ln of x exp of x. Okay, and the green curve is the graph of exp of x. Notice, ln of x has a vertical asymptote at negative y-axis. Because ln of x has a vertical asymptote at negative y-axis, its inverse, exp of x, will have a horizontal asymptote at negative x-axis. Because what's the reflection of negative y-axis? The reflection of negative y-axis across y equals to x is the negative x-axis. So if the graph of ln of x is getting closer and closer to the negative y-axis, then the graph of exp of x will get closer and closer to the negative x-axis. That's how I know that that's the shape of exp of x. Notice ln of x is concave down, exp of x is concave up. That's always the case whenever you have inverses. If the graph of a function is concave down, the graph of the inverse will be concave up. Okay? And we can also see that exp goes to infinity as x goes to infinity. So what is again exp of x? exp of x is the inverse of ln of x. So the domain of exp is the range of ln. The range of exp is the domain of ln. So we know the domain and range of the exp function as well. exp is always positive because the domain of ln is positive, all positive numbers. Now, being inverses, they do the opposite of each other or they undo each other, however you say it. It means that exp function takes x to y if and only if the ln function takes y back to x. In terms of errors, exp takes x to y, ln takes y back to x. Okay? Because they are inverses. Now, anytime you have a pair of inverses, there are cancellation properties. What are the cancellation properties here? Well, if you have a pair of inverses, if you take the composition of the inverses in any order, you get the identity function. Meaning that if I take exp of ln of x, I get x. If I take ln of exp of x, I also get x. But in the first equation, x is in the domain of ln. In the second equation, x is in the domain of exp. Okay? Clear? That's because these two functions are inverses, so they undo each other. Okay? Now comes the point. Remember, what is the meaning of... So let's say r is a rational number. So let's say r is a rational number. What is the meaning of e to the r? Remember at the beginning I talked about what does it mean to raise a number to a rational exponent? I gave you a meaning of that independent of the exponential function. So e is a number, e to the r means whatever I said at the beginning. E to the rational number r. exp of r has an independent meaning, right? exp of r means what? exp of r means is the inverse of ln function evaluated at r. exp of r is the inverse of ln evaluated at r. E to the r is some number, whatever that means from my beginning discussion, and I'm now claiming they are the same. For any rational number r, e to the r is the same as exp of r. Okay, why? Because if I take ln of e to the r, by the third rule, ln of e to the r is r ln of e, but ln of e is 1, so I get r. So ln of e to the r is r, right? ln is taking e to the r to r, so exp will do the opposite. ln takes e to the r to r, so exp will take r to e to the r. So exp takes r to e to the r. So exp of r and e to the r are the same if r is a rational exponent. And that's why it makes sense to define e to the power irrational exponent to be exp of irrational exponent. Am I making sense? It makes sense e to the root 2 to be defined by exp of root 2. This is the definition. E to the root 2 is defined by exp evaluated at root 2. It makes sense to do that. Why? Because for rational numbers r, e to the r and exp of r agree. So it makes sense to say that define e to the x to be ex. So I'm now defining e to the x to be exp of x. I'm defining e to the x to be exp of x for any real number x. So now you have a meaning for what does it mean to raise e to an irrational number x. It means exp of x. So at this point, once I make that definition, e to the x, exp of x, they are synonymous. They are the same. Is it clear? Now, having said that, these two properties 1 and 2, it's important that you write it in terms of e. So number 1 basically now means e to the ln of x. E to the ln of x is x. And number 2 means ln of e to the x is x. Am I making sense? E to the ln of x is x. E to the ln of e to the x is x. What am I doing? I'm basically writing exp. I'm writing exp in terms of e, right? I can do that now. E to the x, exp of x are the same. So I can write the cancellation properties in terms of e now. And they are written in red. Is that clear? Now, what's the derivative of e to the x? The derivative of e to the x is itself, and the integral of e to the x is e to the x plus c as well. I was going to give you a proof again why the derivative of e to the x is itself, but I'm not going to because I need to save some time. You can look into the previous lectures to see why the derivative of e to the x is e to the x. Basically, well, let me not get into that, but you can easily prove that. Now I have the laws of the exponents for e to the x function. If x and y are any real numbers, then e to the x plus y is e to the x into the y, e to the x minus y is e to the x divided by e to the y. And what is e to the x to the power r? This is e to the rx. And what is r here? R here is a rational. R here is a rational number. Okay? Is everybody clear? Is everybody clear now? Now again, number 3 works even when r is a real number, but I'm going to get there in a bit. How would you prove number 3? I want to show you how to prove at least one of them. How do you prove number 3? How would you prove number 3? In order to prove that number 3 holds, I'm going to use ln. I'm going to show that ln of the left-hand side is the same as the ln of the right-hand side. Because ln is 1 to 1, that's going to show that both sides are the same. So what is ln of the left-hand side? What is ln of e to the x to the r? Can you tell me that? Well, for ln, we have the third rule of ln, which says that this is the same as r ln of e to the x, right? That's the third, but I can apply the third rule one more time. This is rx ln of e, which is rx. Now, what is the ln of the right-hand side? What is the ln of the right-hand side? Well, by the third rule again, it is rx ln of e, which is rx again, and these two are the same. So I see that ln of e to the x to the r is the same as ln of e to the rx. And that implies ln is a 1-to-1 function. So if I apply ln to two numbers and I get the same value, those two numbers have to be the same, because ln is 1-to-1. So I see that e to the x to the r is e to the rx. Everybody's okay? You can prove the other ones exactly the same way. Okay? Alright. So we have seen above that e to the x means exp of x. The meaning of e to the x is exp of x for any real exponent x. Okay? But now I want to talk about what does it mean to raise any number a to a real exponent x, right? So what does it mean to raise a to an x, to x, for any x? I have a meaning for a to the x when x is rational, for any a. I have a meaning for e to the x for any real number x. But now I want to say, what's the meaning of a to the x when a is any positive number? So when a is any positive number, x is any real number, what's the meaning of a to the x? The meaning of that is e to the x ln of a. Okay, I am giving a meaning of that in terms of e. Okay? Is everybody clear? Also, if I have a function f of x to the power g of x, as long as f of x is positive, I can say that f of x to the g of x is the same as e to the power g of x times ln of the base f of x. Is that okay? Now, what's the derivative of a to the x? The derivative of a to the x is a to the x ln of a. Is that clear? That's the derivative? Well, think about the derivative of a to the x. That's the same as the derivative of e to the x ln of a. What's the derivative of e to the x ln of a? Well, it's the same thing multiplied by the derivative of the exponent. And if you do that, you're going to get that the derivative is a to the x ln of a. The derivative is a to the x ln of a. Again, I'm going very quickly, but I think I talked about that proof before. Now, what's the integral of a to the x? Integral of a to the x would be 1 over ln of a times a to the x plus c. I think Zach probably said that you divide both sides by, in the derivative formula, if you divide both sides ln of a, you end up with the integral formula. So you get 1 over ln of a times a to the x plus c. That's the integral of a to the x. Now, I'm not going to go over the details, but we also came up with the limit as x goes to infinity of a to the x. When x goes to infinity, a to the x goes to infinity. If a is greater than 1, it goes to 0 when a is between 0 and 1. The limit as x goes to negative infinity of a to the x is 0. If a is bigger than 1, it's infinity. If a is between 0 and 1. Knowing the limits, knowing the derivatives, we know the concavity, know the increasing, decreasing behavior, and I can write down the shape of the graph of a to the x. What's the graph of a to the x when a is larger than 1? The green curve. Concave up, increasing at infinity, going to 0 at negative infinity, right? Concave up. What else do I know? If a is bigger than 1, then 1 over a is less than 1. What's the graph of 1 over a? The graph of 1 over a is the pink curve. The graph of 1 over a is pink curve. Now, if I give you, what would be the graph of, let's say, 1/3 to the x? Or what would be the graph of 0.01 to the x? Will it look like the pink curve or the green curve? Pink curve. The graph of 1/3 to the x and the graph of 0.01 to the x will look like the pink curve because the base is less than 1. The base is less than 1. And in the pink curve, 1 over a is less than 1. Okay? And you can look into that yourself. Okay? So I'm going to delete that for a second here. Okay, so now we know the graphs of those. Now I understand a to the x function, right? What now? The laws of the exponents. Now here, x and y are any real numbers. A and b are positive real numbers. X and y, any real numbers. A, b are positive real numbers. Okay? What are the properties of the exponents? A to the x plus y is a to the x plus a to the x times a to the y. A to the x minus y is a to the x over a to the y. A b to the power x is a to the x, b to the x. A x to the y is a to the x y. Is everybody clear? Now, I'm going to show you a proof of 4, and all the other ones are proved the same way. Okay, so what is a to the x to the power y? What is the meaning of that? I am going to think of this as base a to the x exponent y. Base a to the x exponent y. By definition, what is that in terms of e? In terms of e, it is e to the exponent y, ln of the base a to the x. Right? Now, remember, one of the properties of ln is what? This guy can be put as in the exponent, right? So now I can say this is the same as, I can say that this is the same as what? Well, let me do one more. Let me change that. Let me do one more step here. So this is the same as e to the y times x ln of a, right? Is it okay? This is one of the properties of ln. But now, can you say that, now I think of this as a factor here, can I put that as a power of a? E to the ln of xy. Sorry, not ln of xy. I can say ln of a to the xy. Right? Again, I'm just using the property of ln. And this is equal to what? This is equal to a to the xy, and that's because e and ln, they are inverses. Cancellation property says this is a to the xy. And am I done? Yes, I got the right hand side. Am I making sense? I'm just using the properties of ln to prove this. So you can prove all the other 1, 2, 3 in the same way. Okay, same way. Write both sides in terms of e and apply some of the properties of ln. Is everybody clear? Everybody's clear? Okay, now I have the a to the x function. I want to get to the general log. So what is log base a of x? Log base a of x is the inverse of a to the x. As long as what? As long as a is not 1. If a is 1, log base 1 does not make sense. Because if a is 1, a to the x is 1. If a is 1, a to the x is 1, you get the worst possible candidate for one-to-one function, right? So in that case, a to the x is not one-to-one, right? When a is 1, it's a fake exponential function. It's not a one-to-one function. So the inverse of a to the x is log base a of x. And so what's the domain of log base a of x? The domain of log base a of x would be 0 to infinity, because that's the range of a to the x. Remember, a to the x is always positive. A to the x is always positive. Whether a is less than 1 or greater than 1, doesn't matter. Think about the graph of a to the x. And what's the range of log base a of x? The range of log base a of x is negative infinity to infinity, because that's the domain of a to the x. And then, remember, being inverses, right? If the log base a takes x to y, then the exponential base a takes y to x. Log base a takes x to y if and only if the exponential base a takes y to x. They do the opposite. The way it looks like, it seems like what we are doing is, well, it doesn't seem like, it actually is, that when you are, what is log base a of x? Log base a of x is the power of a that gives you x, right? Log base a of x is the power of a that gives you x. I think that's how people, when I studied this log function in my 9th grade, that's the definition was given to me. That what is log of x base a? Well, the log of x base a is the power of a that gives you x. The power of a that gives you x. Right? Power of a that gives you x, that power, the exponent y, is the value of log base a of x. Which is fine, nothing wrong with it, but it doesn't give you the entire story. So we are looking at the entire story of these two functions. Now, again, if log base a takes x to y, then the exponential base a takes y to x. Because inverses do the opposite of each other, undo each other, however you want to say it. Cancellation properties, being inverses, if I take the composition of log base a and the exponential base a, I'm going to get the identity. Meaning, log base a of a to the x is x, a to the power log base a of x is also x. These are the cancellation laws. And you absolutely have to know these two properties. Okay? What's the derivative of log base a of x? What's the derivative of log base a of x? It is 1 over x ln of a. And if I take the second derivative of log base a of x, I get negative 1 over x squared ln of a. Now I do want to speak about how I got that derivative, because whenever you have a pair of inverses, if you know the derivative of one of them, you can find out the derivative of the other one by the process that I'm going to employ now. And this is important because you're going to do the same thing for finding the derivative of hyperbolic sine, hyperbolic cosine functions, and so on. So here's what that is. So I'm going to look at the proof of the derivative. How? Well, I'm going to let y to be log base a of x, and then I'm going to say a to the y is equal to x, because log base a of x is the inverse of a to the x. So if y is log base a of x, then a to the y is x. Now employ implicit differentiation. By implicit differentiation, I'm taking the derivative of both sides with respect to x. What's the derivative of x with respect to x? 1. What's the derivative of a to the y? Remember the derivative of a to the x? It was a to the x ln of a. So what's the derivative of a to the y? A to the y ln of a. However, am I done? I am taking the derivative with respect to x, not y. So I have to multiply by y prime. So what is y prime then? Y prime is 1 over a to the y ln of a, but a to the y is x, so I get x ln of a. And that's exactly the formula that I gave you, right? The derivative of log base a of x is 1 over x ln of a. Everybody's okay? Now the laws of the general logarithm. Law number 0 is not usually written as a law, but I'm going to write it as a law. What is log base e of x? Log base e of x is ln, because remember, ln is the inverse of e to the x, and log base e is the inverse of e to the x. Log base e is the inverse of the exponential base e. So log base e is the same as the ln function. What is log base a of xy? Log of x plus log of y. What is log base a of x divided by y? Log of x minus log of y. What is log base a of x to the alpha? It is alpha log base a of x. And here I'm saying alpha could be any real number. Remember, I kept saying law number 3 applies more generally for any real exponent, not just rational exponent. And I'm stating that now. And then number 4, log base a of x is ln of x over ln of a. Log base a of x is ln of x over ln of a. Is everybody clear? Questions, comments on these 4 properties? Any questions on this? All right, so let's try to, I'm going to finish up. This is it. We have looked at all the different things that we have to know about these three functions. I just want to end by sort of talking about how to prove number 3. Remember, I proved number 3 for ln function. How did I prove it? I took the derivatives of both sides and showed you that they are the same, and then the constant, whatever comes up, is 0. And I can do the same thing here. However, let me try to do something different, okay? Because I have shown you the other way, let me show you this in a different way. It's a proof of 3. Proof of 3. So how would you prove this? I'm going to let y to be log base a of x. Okay? So what does it mean in terms of in terms of, okay, so that implies a to the y is what? A to the y is x. Is everybody okay with that? All right, so what is then, let me write it here, what is then x to the alpha? X to the alpha would be a to the alpha y, right? I'm raising both sides to the exponent alpha. Raising both sides to alpha, and I get a to the alpha y is x to the alpha. So finally what I have here is a to the alpha y is equal to x to the alpha. But what do I want to show? I want to show that the log base a of x to the alpha is alpha times log base a of x, right? So let me write it down one more time like this. X to the alpha is a to the alpha y. Okay, so now let me say this is equal to what is a to the alpha y? What is yes? So now I'm going to write it as a to the alpha okay, so give me just 1 second here. I want to show log of that. Give me 1 second here. Okay, I don't know why my brain is shutting down on me like this, but remember what I said. You can take the derivatives of both sides and show that they are the same and prove it that way, but I just thought I had a different way here. Just give me 1 minute here. X to the alpha is a to the alpha y, and I want to show log base a of x to the alpha is alpha times, basically alpha times y. Oh, okay. Now, you know what? I'm actually done here. Can someone give me the punchline? Remember, I have x to the alpha, this quantity. I have this quantity is equal to a to the power something. A to the power something is x to the alpha. By definition of log, the exponential base a, taking something, taking alpha y to what? X to the alpha. Exponential base a is taking this quantity to here. So what does it mean for in terms of log? What does it imply in terms of log? It says that log base a of x to the alpha is alpha y. What I'm saying is that the exponential is taking alpha y to x to the alpha, right? This quantity alpha y is going here. So the log will do the opposite, right? The log base a will do the opposite of what you have. So the log base a will take x to the alpha back to xy. Am I correct? They are inverses. Once again, the exponential base a taking alpha y to x to the alpha. So the log base a will take x to the alpha back to xy. So I get this. But however, what is that? What is that? This is log base a x to the alpha is equal to alpha times what is y? Remember, we took y to be log base a of x. We took y to be log base a of x, and I'm done. Okay, that's what I wanted to show. This is without using the derivative. However, you could have used derivative here as well, just like I did before, and you could have proved it that way. Okay? All right, thank you.